This is Chapter 6, Section 6.3, which is separation of variables and the logistic equation, and Section 6.4, first-order linear differential equations. The primary thing that will be focused on in Section 6.3 is separation of variables, which you may or may not have experienced a bit in Calculus 1. But basically, separation of variables is getting the same variables on the same side of the equation. So in this example, we have a couple different examples down here, and then they're rewritten with the variables separated. You could probably see in the rewritten version that all the y's are on one side and the x's are on the other. So it's just using algebra to separate some things. I want to remind you that y prime can be written as dy dx. So in this case, we can write this as sine of x dy dx is equal to cosine of x. And if it is written this way, what we can do is we can multiply both sides by dx. So the dx cancels over here. And then, sorry, lack of room. So then I have sine of x dy is equal to cosine of x dx. And I'm getting closer to separating my variables. The problem is on the left-hand side here, you can see you have x and y. So I can remedy that by dividing both sides by sine of x. The last step is to remember that you can simplify your trig functions. Cosine of x over sine of x is cotangent of x, and that's where that came from. So really, all we are doing is putting all the variables of x on one side and y on the other. So let's take a look at our first example. We are asked to find the general solution of the following differential equation. dy dx is equal to 3x squared over y squared. So we're just going to take baby steps, and I'm first going to break up this by multiplying both sides by dx. So the dx's will cancel, and I'm left with dy is equal to 3x squared over y squared dx. Now I just need to move that y squared to the other side, and I can do so by multiplying both sides by y squared. So the y squareds cancel, and I have y squared dy is equal to 3x squared dx. Now the hard part is done, really, and that's separating the variables. Once the variables are separated, in order to find the general solution, which we learned about in the previous class, we need to integrate both sides. We can only integrate to make our lives easier when we have the same variables on each side. So integrating y squared, we have 1/3 y cubed is equal to x cubed, sorry about that, plus c. Really, you can put a plus c on both sides, but then when you combine that constant, you're still left with a constant. So remember, a general solution is just getting y by itself. So in order to get y by itself, I'm going to multiply everything by 3. So that leaves me with y cubed is equal to 3x cubed plus c. This will suffice. Some people will want to get y completely by itself and take the cube root of both sides. Some people want the constant by itself. If that's the case, you'd have y cubed minus 3x cubed is equal to c. Any of those will suffice. In example 2, we want to find the particular solution. And that means we're going to do the exact same thing that we just did, but we also want to find c. And the way we find c is by using this initial condition that is provided to us. So the first thing you want to do is find, is to separate these variables. So you might want to pause the video here and see if you are able to separate the variables. Looking at this, the first thing I want to do is try to get y prime by itself. So I'm going to subtract this from both sides. And I end up with y prime, which is the same thing as saying dy dx is equal to negative y times the quantity x plus 1. So now, in order to separate the variables, I'll multiply both sides by dx, and then I'm going to divide by y. So when all is said and done, I will end up with 1 over y dy is equal to negative quantity x plus 1 dx. As in the previous video, now that the variables are separated, I can go ahead and integrate both sides. When I integrate both sides, I'll find that on the left-hand side, the antiderivative of 1 over y is the natural log of the absolute value of y, is equal to, now be very cautious of that negative sign there, when you integrate that, you should get negative 1/2 x squared minus x plus c. A lot of people like to get y by itself before applying the initial condition. So if I were to try to get y by itself, I would basically exponentiate both sides, or I always called it the log loop. Take the base of this log, raise it to this power, and it's equal to y. So I'm left with y is equal to e to the power of negative 1/2 x squared minus x plus c. Here I want you to remember properties of exponents. Properties of exponents allows me to rewrite this a little bit. This can be written as e to the 1/2 x squared minus x power times e to the power of c. The reason for this is because the property of exponents allows me to add the exponents if the bases are the same. E to the power of c is simply a constant, and therefore I am left with y equals c, because of that constant, e to the power of negative 1/2 x squared minus x. Now that y is by itself, I can go ahead and apply this initial condition by plugging in negative 2 for x and 1 for y. When I do that, this will allow me to find the value for c. So I'll go ahead and do that now. So simplifying this here, this gives me a positive 4 times a negative 1/2. That gives me a negative 2. This gives me plus 2. So I have 1 equals c e to the power of 0. Remember, anything to the power of 0 is just 1. So I have found that 1 is equal to c. Now I can go ahead and write my particular solution, plugging in what I know for c to be 1. I can go ahead and write the 1 if I want, right here, or I can simply write e to the negative 1/2 x squared minus x. And this here is the particular solution. There are a few applications involved in this section. And really, they talk about a little bit about electrostatics, thermodynamics, and hydrodynamics. If you're interested in learning more about this, there are a couple videos that you can watch. In the OneNote class notebook under videos, chapter 6 specifically, in section 6.3, you can watch the videos involving finding orthogonal trajectories, as well as logistic growth. But There are some applications dealing with orthogonal trajectories. And one thing I want to mention is that orthogonal is fancy for saying perpendicular. So remember, if we know the slope of something, perpendicular lines are opposite reciprocal slopes, and we're going to applying the idea of orthogonal lines being perpendicular and the opposite reciprocal slope, we are going to find the orthogonal trajectories for the family of curves here. So what I want to do is I want to find the derivative of this, because remember, the derivative is fancy for slope. So I'm going to apply implicit differentiation here with respect to x, and that will allow me to find dy dx. So doing so, I end up with 2x minus 4y dy dx is equal to 0 because the derivative of a constant is 0. Now, getting dy dx by itself, I'm going to move the 2x over by subtracting, and then I'm going to divide both sides by a negative 4y. And when I do, I end up with the derivative being x over 2y after simplifying. Recall that dy dx represents the slope of a given family of curves, so the orthogonal family has opposite reciprocal slopes. Because remember, orthogonal is fancy for perpendicular. So if we know that this is the slope of the orthogonal trajectory then will be dy dx is equal to negative 2y over x. Now I'm going to find the orthogonal family by separating the variables and integrating, just like we did in the previous examples. So when I do that, I'm just going to separate these guys, and I'm going to move the x's onto one side. So I'll end up with dy is equal to negative 2y over x dx. I'm going to leave the negative 2 there, but divide by y. So when I do that, I'm going to have 1 over y dy is equal to negative 2 over x dx. And now that the variables are separated, I can go ahead and integrate both sides. When I do, I end up with the natural log of y is equal to negative 2 natural log of x plus c, or I believe the notation they like to use in the book would be plus k. So now what we'll do is we will get y by itself, and the way we get y by itself is by basically exponentiating both sides. Now before I exponentiate both sides, I want to remind you of a property real quick. Recall this here can be written as the natural log of x to the power of negative 1/2, because rules or properties of logarithms, you can take the exponent and move it down in front. So that is a bit helpful. So then if I exponentiate both sides, I end up with y is equal to e to the natural log of x to the negative power of 2 plus k. And I can rewrite this as the following. And then this all will simplify because e to the natural log cancels. E to the k is simply a constant yet again. So I end up with y is equal to x to the negative power of 2 times k, but cleaning this up a little bit, I have y equals k over x squared. And that represents the orthogonal trajectories for the family of curves. In the next slide, we're going to talk about logistic differential equations. Here, these equations represent the exponential growth model. And I want you to notice that the logistic curve here has something that is called a carrying capacity. Technically, exponential growth is unlimited, but if we're dealing with population, you know, the population is not going to increase forever and ever. It's going to have some sort of maximum population. So this blue line here represents the carrying capacity or the upper limit. I would recommend seeing example 6 in your text on page 427. That kind of explains things well. In this example, we will find that the general form of the logistic differential equations looks like this. So if you're wondering where these equations come from, it's found there. So let's take a look at our first example. Here we're talking about the population of rabbits, and it's given by this formula here, where t is represented by the number of months. The first thing you're asked to do here is to graph this function and label your axes. I think it's important that you try to graph this on your graphing calculator so that you can get an idea of how to graph this type of information. So go ahead and pause the video now and attempt to graph this function, and then come back and take a look. Now, when you are graphing this, I would recommend using a window something along the lines of 0 to 40 on the x-axis. Remember, x is going to be t in this case, representing time. I think a scale of 1 or 2 would be fine. Then on the y-axis, I would use 0 to about 1500. And you can scale it by 100 maybe. I chose 1500 because it's a little bit more than the numerator here, which often plays a big role in the decision. When you graph this, P of t is the y-axis, t is the x. Remember, this is months. This is the number of rabbits. And you'll find that the graph looks a little something like this. And just like the graph that I showed you on the previous slide, you can see that there is a carrying capacity. There will be a maximum number of rabbits that the population can achieve. So what we want to do is we want to find the number of rabbits at each of these times. And if you have graphed this, it should be pretty easy for you to calculate these values. The first thing you want to do is find P of 0. So plugging that into your graph, you should find that it is approximately 8.163 rabbits. Finding the number of rabbits after 5 months, P of 5, plugging that into your calculator, you will have approximately 214.165 rabbits. I understand that you can't exactly have a fractional rabbit, so just make sure you're paying attention to how they want the answer written, whether it's to the nearest whole or not. Finally, the population at 9, oops, this should be months, I apologize, is approximately 817.575 rabbits. And again, that's just found by plugging those values into your calculator. And if you need help with that, just let me know. In part C, we want to know when there will be 650 rabbits. So we can solve this graphically. And the way we can solve that is we can write our function in the following way. And what we want to do is we should already have this graphed in our graph in y1. So then what we can do is graph this in y2 and simply find the intersection. So if you do that on your calculator, which I hope you try to do, you will find that the intersection is approximately 7.742 months. And this should make sense because if you look at part B in the previous slide, we know the number of rabbits at 5 months and the number of rabbits at 9 months. And that is, in 650 is in between those. So this does make sense. Now we want to determine when the population growth rate is the greatest. So remember, the rate talks about the slope. So if I want to find when the growth rate is the greatest, I want to find the steepest slope. And there are a few ways you can do this. What you can do on your calculator is graph the slope or the derivative and then find the maximum. Otherwise, you can kind of do a guess and check type of thing and see when the slope appears to be the steepest and do some more calculations. But you should find that this is approximately 6.857 months. Finally, what is the carrying capacity as t approaches infinity? This just means as time goes on, what is the maximum value that the population will reach? And in this case here, there are a couple ways you can identify this. You can identify it graphically, but if not, if you want to see, oops, we're dealing with a variable of t. Just kind of think about limits and what happens if you plug infinity in for t. And really plugging infinity in is a bit of a faux pas, but let's just analyze what's happening here. What happens if you think about this function, this here will end up approaching 0. So e to this power, it ends up being e to the negative infinity. And if you think about what the graph of e looks like, it looks like this. So if you end up having a negative infinity, this function's approaching 0. So just this part here is 0, so we end up having 1,000 over 1, which is 1,000. So the carrying capacity as t approaches 1,000, or I'm sorry, as t approaches infinity is 1,000 rabbits. This example concludes section 6.3. Now we begin section 6.4, which is first order linear differential equations. So here we have the definition of the first order linear differential equation, and it is shown right here. And a couple of things to pay attention to is this p of x. This is just the coefficient of y, so that's important to notice. So p and q are continuous functions, and standard form indicates that the coefficient of y is 1. I'm sorry, of y prime. So here are the steps to solving a first order linear differential equation. The first thing you want to do is write it in standard form, which you can see looks like this up here in the definition. Then we want to identify the functions p of x and q of x. And then we're going to determine the integrating factor. sometimes represented by IF. IF is always e to the integral of px dx. So that's why we want to identify p of x, I'm sorry, not px, but p of x, and then we can find the integrating factor. Once we have that, we'll multiply everything by the integrating factor and then simplify. So I think it's probably best to just jump into some examples of this. So in our first example, it says find the general solution of this here. So looking at this, this is our first order linear differential equation. And the first thing I want to notice is that this is already written in standard form. I know it's written in standard form because the coefficient of the derivative is 1. So now that I know this, the next thing I want to do is I want to identify p of x and q of x. P of x, recall, is whatever is attached to the y value, or the coefficient of y, which in this case is 2 over x. I also want to identify q of x, and that's whatever the function is equal to. In this case, 3x minus 5. Once I do that, step 3 says determine the integrating factor. So if I want to figure out the integrating factor, I know what p of x is, so I'm going to, oops, I apologize, I got ahead of myself. I'm going to find e to the integral of p of x, which is 2 over x dx. Now you may want to take a little bit of time and rewrite this as e to the power of 2 times the integral of 1 over x dx. And then you should be able to identify that this is equal to the natural log. I'm sorry, so this becomes e to the 2 times the natural log of x. Continuing to simplify this, you may want to use the properties of logs and rewrite that 2 as an exponent, so it becomes e to the natural log of x squared. The reason I want to do this is because the e and the natural log will cancel out, giving me an integrating factor of x squared. Okay, so now we have done step 3 in the previous slide. Now what I want to do is I want to multiply the entire equation, so the entire standard form equation, by the integrating factor. So here we go. In step 3, we're going to multiply everything here by x squared. So we end up with dy dx times x squared plus 2 over x y times x squared is equal to the quantity 3x minus 5 times x squared. And now we want to simplify. And there are a couple things to pay attention to when you simplify. And the first thing I want to focus on is this part here. When I simplify this, oh, I apologize, this entire left-hand side of the equation. When I simplify this, I will always end up with y times the integrating factor, in our case, x squared, the derivative of that quantity. This is always, always, always. And that's why I put a couple stars on the previous slide by simplify. So take note of this. Then I'll distribute this x squared, and this is equal to 3x cubed minus 5x squared. Now I can go ahead and integrate this. When I integrate this derivative over here, remember the integral of a derivative cancels one another out. So this simply leaves me with the integrand, which is x squared y. And I just reversed the order of those variables. And then integrating the right-hand side, you should end up with 3/4 x to the 4th minus 5/3 x cubed plus c. Now, I want you to recall, if I'm trying to find the general solution, I want to get y by itself. So if I'm trying to get y by itself, I'm going to divide everything here by x squared, which is the same as multiplying by 1/x squared. So when I do that, I end up with y is equal to, this little piece here gives me 3/4 x squared, because some of the x's cancel. Same type of thing here, negative 5/3 x plus c. If you want to write the c over x squared, you certainly can, but that just remains a constant anyway. So that is an example of finding the general solution. So now in the next example, we want to find a particular solution. This is the exact same thing we did, but there's just one additional step. And in that one additional step, what we want to do is plug in this initial condition in order to find C. So everything else is the same. So what I'd like you to do is take a moment and pause this and find the integrating factor if possible. Okay, recall, if you want to find the integrating factor, remember the coefficient of y prime needs to be 1. So I'm going to go ahead and divide everything by x cubed. So when we do that, then I end up being able to identify p of x and q of x. So if I look at this, p of x is 2/x cubed. So if I want to find the integrating factor, I will have e to the power of 2 times the integral of x to the negative power of 3 dx. And I hope you have followed what I did there. I just kind of rewrote it so I could integrate a little more effectively. So then this gives me, let's see, if I'm just going to focus on the integration part real quick. So if I integrate this, I end up having 2 times negative 1/2 x to the negative power of 2, which simplifies to negative 1/x squared. So my integrating factor then is e to the negative 1/x squared. So remember, you are going to multiply everything in the standard form of the equation. You're going to multiply that by the integrating factor. So let's go ahead and do that now. So when I do this, I'm going to have y prime times e to the negative 1/x squared plus, I'm going to multiply this by the same thing. So this is 2y/x cubed times e to the negative 1/x squared is equal to, now this here I'm going to write as 1/x cubed times e to the 1/x squared. I am going to multiply this by the integrating factor, which is e to the negative 1/x squared. Now, the nice thing here is some things cancel. Since these have the same base, you can add the exponents. When you add the exponents, you get a power of 0, and anything to the power of 0 is 1. So what happens is these cancel out, and you're only left with 1 over x cubed on the right-hand side. Remember, the left-hand side always becomes the derivative of the product of y times the integrating factor, which in this case is written here. This is equal to 1 over x cubed. Now I can integrate both sides. Integrating the derivative cancels everything out, leaving me with this. And then on the right-hand side, I end up with a negative 1 over 2x squared plus c. Again, I want to get y by itself in order to have a particular solution, so I'm going to divide everything by this. If I divide by e to the something that has a negative power, that's like multiplying by a positive power. So this becomes y equals e to the positive 1 over x squared times everything else here. So that is my general solution. But now I want to find a particular solution. So if I want to find the particular solution, I'm going to use this and plug in these values. Here, x is 1 and y is e. So I'm going to plug that in right here. And when I do, I end up with the following. E is equal to e to the power of 1 times negative 1/2 plus c. Now, I want to try to find the value of c, so what I'm going to do is try to get rid of this e, and I'll do that by dividing by e. So I have 1 equals negative 1/2 plus c. I'll add 1/2 to both sides, and I find that 3/2 is equal to c. Once I know that, I can go ahead and plug this back in here for c, and then I will be done. So my answer will be y equals e to the 1 over x squared times negative 1 over 2x squared plus 3/2. And that is the final answer. Wasn't that fun? Now we're moving on. Okay, so here we have a falling object example, and it says consider an object with a mass of 4 kilograms dropped from a height of 1,500 meters, where the air resistance is proportional to the velocity. Write the velocity of an object as a function of time t when the velocity after 5 seconds is approximately negative 31 meters per second. What is the limiting value of the velocity function? Now here I want to mention an example in the text. From example 3 in the text on page 434, that gives us some information about falling objects. That tells us that the velocity, or v, is equal to the following. Negative m times g over k times 1 minus e to the negative kt over m. This information tells us that g is the acceleration due to gravity. And if we're dealing with meters here, the acceleration due to gravity in this case is 9.8 meters per second squared. So if we know that, then we know that mg is equal to 4 times 9.8 because the mass is 4 kilograms. And that gives us 39.2 after multiplying. So now what we want to do is we want to use this information here and plug that information in. So if we know that v of 5, because the velocity after 5 seconds is 31, we can go ahead and plug that in. So our equation becomes -31 is equal to -39.2, which we just found, over k times the quantity 1 minus e to the negative k times 5 all over 4. Now using a graphing utility, we can go ahead and find the value of k. So what we can do is we can graph this in y1, this in y2, and find the intersection. So we can find that k is approximately 0.7984, and you will absolutely want to try to do this in your calculator. So go ahead and pause this and try to find that value. Once you have that, you might want to store it in your calculator in order to not have any errors in your approximation. But once you have this, now what we need to do is work toward finding the limiting value. Okay, so now basically what I'm going to do is something similar to what we did in a previous example. I am basically interested in finding the limit as t approaches infinity of this function once k is plugged in. So if I want to find this, then basically plugging in all of my information, we know this is k, and this is an approximation. You're going to want to use the exact value if possible. This is divided by 4, and then we'll multiply this by t. All right, so a little bit of simplifying ends up giving us this. Okay, and so let's analyze this for a second. Just looking right here, and we want to know, again, the limit as t approaches infinity. So I just want to remind you that the graph of e to the x looks like this. So the graph of e to the negative x looks like this, which is really what we have. And if you look at this, as x or t approaches infinity, this value is approaching 0. So all of this here is approaching 0. So I have this times 1, which tells me that my limiting value is approximately -49.099. And again, that is the limiting value of the velocity here. Oh, I should tack on meters per second since we're dealing with velocity. And that wraps up this lesson.